Now let's discuss about the merge sort. Right? So this is the first divide and conquer sorting algorithm we are discussing, and it is developed by John von Neumann in 1945, right? The merge sort is one of the earliest sorting algorithms to achieve n log n complexity, time complexity, and its guaranteed performance have made it a fundamental algorithm in computer science, education and practice, right? The core idea behind the merge sort is simple. It means split the array into two halves and recursively sort each half, and then merge the two sorted halves back together, and then the merging step where two sorted lists are combined into one sorted list efficiently. So let me give an example. Imagine you have two piles of playing cards, each already sorted from lowest to highest. You want to combine them into a single sorted pile, and you would simply compare the top cards of each pile and then take the smaller one and place it in the new pile, right? You repeat this until one pile is empty. Then add all remaining cards from the other pile. This is exactly how merge sort works, but on a much larger scale, right? So let's look at an example. So the merge operation is the heart of the merge sort. It takes two sorted arrays and combine them, right? And let's examine the process in detail. Here you have 38, 27, 43, 3, 9, 83, 82 and 10, right? These are the array elements, right? So what we do initially, we divide the array into two halves, right? You can divide this here, right, or here, and just divide, okay? And then what you can do, again you can divide this into two halves, right, like here, and you get 38, 27 and then 43. Here you divide 3, 9 and 82 and 10, right? And again you divide until you get these elements alone, right? So you have 38, 27, 43 and 3, 9, 82 and 10, right? And you have to, now you have to do what you have to do. This is like a recursion tree, right? Now you have to merge, right? So when we merge, we first compare these 11, right? 38, 27, which is the smallest element, 27, right? So we sort it and combine. Then we had 43, it's in the second level, right? Just like in previous case. You are going from top to bottom of the tree, and then to merge we go bottom to top. That's what this does, right? And we have 3 and 9 here. After sorting we get 3 and 9, okay? And we have 82 82 and 10 here. After sorting we get 10 first, which is smaller than 82, and 82 here. Okay, then from this step you have to combine these, right? Left subtree and this is the right subtree. Okay, this is the left subtree element, this is the right subtree elements. Here also you have to combine initially the left subtree and then the right subtree elements, right? So 27, 38 and 43, which is the smallest element? 27, right? Then what's the smallest element? 38, and then finally 43. Similarly here also you have 3, 9, 10 and 82. We combine the smallest to the largest, right? We have then 3, 9, 10 and 82, right? Now we have sorted the left subtree and the right subtree, right? So now we have to combine into a get the full array. Okay, so which is the smallest element here? 3, right? And then 9, and then 10, then 27, then 38, 43 and then 82. That's the idea, right? Merging two already sorted arrays in one sorted array. For example, if you imagine you have 27, 38 and 43, and then 3, 9, 10 and 82. If you had to merge these two, what can you do? So you need to compare the first elements in both arrays, right? It means compare this and take the smallest one and move the pointer forward and repeat until one array is empty, right? And then you have to append the remaining elements. Let me discuss it. So you had 27, 38, 43, 3, 9, 10, 82, right? This is the left array, this is the right array, right? So initially we check the first elements, right? So 27 and 3, which is the smallest element? 3, right? So we get 3 here, right? Then what do you do? Keep this pointer as it is, as we haven't take this value, and we shift this pointer to 9, the second element, right? Then we compare these values, right? So which is the smallest one among 9 and 27? 9, right? So we get 9 here as the second element, right? And again, what pointer you need to shift? This pointer, right? As we haven't take this value, we have to shift this pointer, right? And we compare 10 and 27 again, right? So which is the smallest element? 10, right? So we insert 10 here. Then again you have to shift the pointer, right? So what need to be shift? 27 we haven't keep the pointer as it is, and we have taken 10, right? So the 10th element is not there now. we have to shift the pointer to the right, and then we get the pointer pointing towards the 82, right? Now we compare 27 and 82. So which is the smallest one? 27, right? So we insert that value here. Then again, you haven't take this value, keep the pointer as it is. You have take this value. Now you have to point the pointer one step right? So we have now pointing the pointer to 38. We compare 38 and 82. Which is the smallest one? 38, right? So we insert that value. And again, which pointer you need to shift? We got 38, right? So the pointer should point to the next element. And we compare 43 and 82, which is the smallest? 43, right? So we insert that value. Now this thing is empty, right? This array, left array is empty, and the right array has one element. So final step is, what's the final step? Append remaining elements, right? So we have the 82 as the remaining element. You just insert it, right? Append it, right? So the final merge array, the sorted array is this. Okay. So let's discuss about the pseudocode. So the base case here handles the array of size 0, 1 element if they are already sorted, and we calculate the middle point, which is left plus right, and divide by 2, right? So as we discussed earlier in the example, we divide the array into two halves and recursively sort both the halves, right? So that's what this does. Sort the left half, sort the right half, and then we merge it. So in the merge function, what happens is this, right? This is just the pseudocode, right? You can try using example and check whether this works, right? Okay, and this function demonstrates several important programming concepts, which has 3-pointer concept and 3-pointer technique for merging two sequences, and we can efficiently handling of remaining elements, and use of temporary array to merge the merge operation, right? So now we will be discussing about the merge sorts complexity, right? So the time complexity of merging merge sort is determined by its recurrence relation, right? So let me analyze it carefully. Where Tn, time complexity, is 2Tn divided by 2 plus On. So 2Tn divided by 2, it means 2 recursive calls in half the size, right? So the time complexity goes for 2 recursive calls on half the size, right? And On is for merge step, which is n comparisons and 2n data movements, right? To solve this recurrence, we can use the master theorem, right? And for example, label 0, which is top, the original problem of size n. Does ON work in merging, right? So in level 1, two subproblems when we divide the array into two halves, which has n by 2 elements, and each do ON divided by 2, right? Total ON, right? And the level 3, you have 4 subproblems, right? Likewise, it becomes n divided by 4. So each doing O n by 4 work, right? The complexity, it becomes ON, right? So likewise, the recursion depth is around log to n, right? Log to the base n. And each level we do ON amount of work. Therefore, the work is ON log n, right? So consider this example. Here we have 2, 8, 9, 3, 11, 5, 4, right? So you can split this into halves. Here you have left subtree as 2, 8, 9, right subtree as 3, 11, 5, 4. Okay. And you again have to split the array into two halves, right? We have now 12 and 8 and 9 here, right? Again split. You have no elements to split here. You split the right subtree of the left branch, right? So after splitting, you have these elements, right? So now you have 8, 9 and 12 as the elements, right? So we have to, what we will do? We do merging, right? So what's the smallest element among these? 8, right? And then 9, we combine them, and then we compare 12 and 8 and 9, right? So what's the smallest element? 8, then 9 and 12, right? Just like the left subtree, you can split and merge the right subtree, right? Then we compare the outputs of the left subtree and right subtree, and again we merge by comparing them, right? Now you can try these questions. Take some time and do these questions. So the first question was, trace the merge sort algorithm on the following array, right? So what we will do? We have 15, 7, 22, 4, 18, 11 and 9, right? We split the array into two halves. This is what it does. This is the left tree, this is the right subtree, right? Then again you have to split from here, right? We have now 15, 7, 22 and 4. So likewise you have to divide, and then finally you have to merge, right? First we combine these two elements, 15, 7, and from smallest to largest Then we again combine these two elements, smallest to large, and again this likewise we combine, and then we combine these two elements again, right? Two subarrays again. We have this and this. This is the left subtree output, this is the right subtree output. Then we combine and we get the finally sorted array, right? The second question, given the following two sorted arrays, right? You can see the difference, right? You have subarrays, two sorted arrays, and you need to combine, right? What we will do, in step 1 you have the pointer in here, right? Here and here. For the left array you have the pointer here, for the right array you have the pointer here, right? So we compare these two elements, 2 less than 3, right? So we pick 2 and we create the array, merge the array, and insert the element 2 there, right? Then the second step is, now you took the 2, now you have to move the pointer to right? So now we compare 5 and 3, right? We don't move this pointer because we haven't taken this value, right? And we have the pointer here, which is the smallest one, 3, right? So we insert the value 3 to the merged array, right? So likewise you can fill this table, right? Finally you will encounter a remaining element, you just need to append those, right? So the final merged array is this. And the third question is, consider the following recursive call, and what portion of the array is being sorted, right? And then what does 0 represent, what does 7 represent, what is the major operation performed by the merge sort algorithm after the function call, what happens after the recursive division is complete, if the array has 8 elements, how many elements are included in the initial function call. So what portion of array is being sorted? This is called the sorted portion of the array from the index 0 to 7, and 7 is inclusive, it means it goes up to 0 to 6, and the initial call to sort an array is of 8 elements, right? So the 7 is inclusive, right? And the 0 is the starting index and the 7 is the ending index, okay? And what is the first major operation performed by the merge sort algorithm after this function call? So what we will do, we initially recursively divide the array into halves until single elements are reached, right? What happens after the recursion division is complete? Divide when then it will be merge the two halves into sorted order, right? Finally So if the array has n elements, how many elements are included in the initial function code? So the merge sort sorts the first 8 elements of the array, right? That's what it does. This is the Python code for the merge operation, and you can test it in any language. This is for simple understanding, right?